checks because they're doing photo ops in the suit up room. But you know, after going through a scrub the next day, you know, everything's pretty fresh. The nerves aren't as there as much. You still have that blender of emotions that you're going to be going through, but you're ready to go, and you can tell the mood is positive, and they are excited to get out there and
always going to be very important for decades to come. And when it comes to technology, we're not waiting around. We're discovering new ways to grow crops in harsh environments and engineering innovations to tackle Earth's greatest challenges.
We have amazing technology that allows us to recycle water and create water for us to drink. It's delicious.
Microgravity isn't just a curiosity, it's a game changer in the fight against diseases back on Earth, paving the way for breakthroughs that benefit us all and enabling new economic opportunities in space.
Welcome. Axiom 3 on board the International Space Station.
From our vantage point more than 200 miles above Earth, we are not just spectators. We're gaining unprecedented insights into the world we call home, and we're sharing our findings openly. We're not just achieving results today. We're sparking inspiration in future generations of explorers and embracing the power of global collaboration as we reach for the stars.
What was your favorite experiment on the International Space Station?
Toby, great question. My favorite experiment was the one that I got to eat. It was us growing Hatch chili peppers in our plant habitat.
Station Huntsville on 2, we have video in Node 1. Look at those chili peppers.
And as we soar through space at 17,500 miles per hour, each moment is a step closer to unlocking the mysteries of our Earth, our universe, and propelling our pioneering spirit even farther into space. So come along for the ride aboard the International Space Station.
The beauty of the International Space Station and all the science that's happening aboard.
Yeah, I mean, that's it. Why are we there? It's science. It's science in the space environment and in the radiation environment. It's science in microgravity, where you can float without end, and you can't do that anywhere else.
Well, as you can see from this shot, looking skyward, up past the Falcon 9 rocket and Endeavour spacecraft, our astronauts are aboard. They are strapped in. They've had suit leak checks. They've had comm checks. And we're starting to get a few little clouds in the sky. That's expected. It's warm here in Florida on this first day of August. And it's also very humid, even more humid than it was yesterday. As you can see, the puffy cumulus clouds are accumulating a little earlier today. While we have this moment where we have a natural pause in the action, let's take a look at our crew today and introduce you to the entire team. They are led by Crew 11 Commander, NASA astronaut Zena Cardman. She holds a Master of Science in Marine Sciences from UNC Chapel Hill. Cardman has experience with NASA research in the Canadian High Arctic and has supported real-time station operations and lunar surface exploration planning. She also likes rock climbing and powerlifting in her free time. And you trained with her for over a year.
Yeah, almost 18 months. She's a person of many talents. But most importantly, she's got an infectious personality. Her positivity and she's just a fun person to hang out with.
It does. It radiates from her.
It does. Yep.
You know?
Yep. And that's, if you're going to be in a capsule for 15 hours or 20 hours or 40 hours, or you're going to be in a station in close proximity to somebody for 6 months or more, you want somebody that you enjoy hanging out with.
And I certainly enjoyed our time together when she co-hosted our launch broadcast for Crew 9, when we watched you, Nick, go up into space. Michael Fink is our pilot and funny man. Only, according to him, the only second funniest crew member aboard. He is a veteran of 3 space flights. Fink has completed 9 spacewalks, totaling 48 hours and 37 minutes of EVA time. He spent 382 days in space. Fink is a certified pilot for Boeing Starliner and SpaceX Crew Dragon, as well as a co-pilot, flight engineer on Soyuz, and a mission specialist on the Space Shuttle. Fink enjoys spending time with his family, traveling, geology, and learning new languages.
Equally, somebody that's enjoyable to hang out with.
That's true.
It's, you can say that about all of this crew. Just
Dragon
great
SpaceX,
people.
we had a good side hatch leak check.
Dragon copies. Good leak check. Great news.
That is great news.
That is. And so that that means that the crew is sealed up inside, safe from the hostile environment of space once this Dragon spacecraft gets into
Dragon SpaceX
gets into orbit.
We are commencing health check for launch escape system. Expect momentary flight computer state change, followed by a transition back to pad hatch closed.
Dragon copies. We'll monitor the flight computer state changes.
Now, this is an important milestone to check the health of the launch escape system.
Yeah, absolutely. And we're doing it well in advance of when, you know, we would turn on the launch escape system and activate it at about the T-45 point before you start to add your propellant and your oxidizer to the rocket. You want to do that early, so if there is any issues you need to troubleshoot, you've got time to do it. So this is the early checkout of that system.
Let's introduce you to our mission specialist now. Kimiya Yui is the JAXA astronaut on board. He's Crew 11's mission specialist, and with 142 days in space, this will be Yui's second trip to the space station. Yui flew as a flight engineer for Expedition 4445 and became the first Japanese astronaut to capture JAXA's H-2 transfer vehicle. In November of 2016, Yui was assigned as chief of the JAXA astronaut group.
Yeah, when you think about his history, you know, capturing the H-2, the HTV, it'd be pretty spectacular if he could capture HTVX as it comes up.
Absolutely, and that's the plan. So if HTVX, which is Japan's newest vehicle, which is going to start docking with the space station, if it all works out, JAXA is really hoping that he'll be at the helm of the crew, or I'm sorry, the Canadian arm, which will grapple the spacecraft and bring it in to space station.
That'd be fabulous. You know, the international aspects of the space station can't be, you can't overstate the importance of it. It's just the way we're able to collaborate and cooperate together, you know, using the Canada arm to grab a JAXA vehicle.
Dragon SpaceX 4.
And so some of her personal items have been up there since over a year ago. And,
Wow.
and so part of it was when we got up there, making sure that we were able to set her things aside.
In Florida. Our launch director will also check in with the Dragon mission director, referred to as MD, and the NASA launch manager to make sure they're ready to move forward as well. Of course, our Crew 11 astronauts right now are on board Dragon, waiting to get the green light to stow the crew arm for launch and arm the launch escape system. Got some great shots of our astronauts on the left-hand side of your screen right now, and of course, they are safely tucked inside Dragon on the right-hand side. Once we hear that launch director give the go-ahead, we'll get a great view of that access arm moving away from the spacecraft. We are going to stand by here and listen in for that final poll and some instructions to our team in that final lead up to liftoff.
Poll for propellant load and launch is complete. Stand by for briefing on control room procedures. For all operators at MCCX and Hangar X, both control rooms will go into lockdown at T-minus 45 minutes and will remain in that state until LES is disarmed. All operators are to remain at their console and maintain a sterile cockpit until MD confirms successful disarming of the launch escape system following orbital insertion or propellant offload in the event of a scrub. For non-urgent no-go conditions, brief the CE or LD and they will approve aborting the count. For urgent issues affecting the safety of the operation, operators shall call hold on the countdown net. Launch control will abort the launch auto sequence immediately and proceed into launch abort. At T-minus 10 seconds, launch control will be hands-off and relying on automated abort criteria for the remainder of the count. Operators advise launch director whether structural breakup or fire is imminent or occurring per Dragon manual flight escape rules. Launch control, you may proceed with arming the crew arm for movement.
Arming crew arm now.
So we just heard those instructions to our team. Again, we're about to see that crew access arm move away from the
Crew
spacecraft.
access arm retraction started.
Starting right now. And with that, propellant loading is going to get underway here in a little bit less than 10 minutes. So with that, let's check back in with Daryl and Nick.
And you can see now the crew access arm articulating away from the Dragon Endeavour, where our crew of 4 is inside. That's a beautiful shot there. A big milestone after getting the go from the launch director at SpaceX. A look from inside the crew access arm now and out over the Space Coast. In this moment in between having the crew access arm rotate away and the arming of the launch escape system, there's a little buffer there where the astronauts will be on their own until that can be armed. And then we start tanking the rocket.
Right. So everything is leading up to
Crew access arm retraction
adding
completed.
the propellant, adding the oxidizer, filling those tanks on the rocket. And so what do you need to do to be safe for that? Well, I need to arm the launch escape system, but I don't want to do that when the arm is right next to the capsule. So I need to move the arm away. Now I can arm the launch escape system, and then we can start filling the rocket.
T-minus 41 minutes and counting here at the Kennedy Space Center in Florida.
SpaceX, you are go for section 6, close visors and arm launch escape system.
Copy, go for section 6, closing visors and arming launch escape system.
Here's a beautiful shot from our helicopter looking west. You can see the formation of cumulus clouds in the area. Weather is a watch item for today. The launch weather officer.
Dragon, visors closed, arming launch escape system.
SpaceX copies.
The launch weather officer putting it at 60% go for today. The concern is the buildup of cumulus clouds, the ones that you see there building up. There's a lot of moisture in the atmosphere. But although you see those clouds around the pad, notice as we start to circle around to the west and look east, clear skies out over the Atlantic Ocean. So when you look at this picture, Nick, you can certainly understand that even though we have clouds that are building in the area, there's an area that we can find over top of this launch complex that we could potentially
System is verified armed.
Get clear enough path to launch this rocket.
Yeah, you just need a hole big enough to launch through. So you don't have to have cloudless skies.
Dragon.
You just need clear enough skies.
Clear enough 10-mile hole would be nice.
I think if we think enough positive thoughts here at the launch site, we can create that bubble.
I'm working on mine.
Me too.
And so we've been listening as they walk through the milestones here, the arming of the launch escape system. This is a critical system. Nick, you know this very well.
Yeah, it's an absolutely critical system. We're just moments away from them getting ready to tank the rocket, fill it up with the kerosene and the liquid oxygen, and before you start to do that procedure and load all of that stored energy onto the rocket, you arm the launch escape system so that if anything goes wrong in a heartbeat, that system can pull that capsule away from the rocket and off to safety.
Commander Nick Hague, when you were commanding Crew 9, you sat through these very same moments in the Dragon, on the launch pad, ready to go.
Yeah, once you once you press the button to launch, to arm the launch escape system, there's a switch in your mind. Now you're sitting on a live rocket. Now everything is primed and ready to go. You are definitely focused on everything leading to T-0 and liftoff.
And that arming of the launch escape system happening just a few seconds from now. We expect it at T-38 minutes. And again, that allows the Draco engines on the Dragon to pull that spacecraft away in the event of an emergency.
It's a beautiful view. One of the things I love about the way Dragon fills its tanks is being able to watch the frost build up when these cryogenic fuels, when you load them onto the rocket, you're going to see it change color. It's a unique experience for
Kennedy Space Center in Florida. And as you can see, work is well underway for our next.
And I'll stay positive.
And you've been positive. I appreciate that about you. You've done that throughout the broadcast. Here's a look from our helicopter.
That same speech he went on to say,
See here TAGSAM putting the sample into this canister, and then in the year 2023, September 24th, this will parachute through and actually land on the Utah desert. So what we're going to do now is actually go into the mission support area here at Lockheed Martin. So how much time do we have now?
It looks like we have about 40 seconds or so before we start seeing the actual burn.
So just to remind you that we're live here at Lockheed Martin, and we are just about to arrive at the asteroid Bennu and begin proximity operations to study this asteroid, eventually returning a sample back to Earth.
It's so exciting. I can't believe we're here. All stations, stand by. Burn has started. Stand by for Bennu arrival. So you can see here we have the Doppler residual, so the burn is occurring because I'm seeing a change in velocity from the spacecraft.
It's going to be very quiet here. Everything's just good.
We have arrived.
You may have noticed we were doing a bit of an unusual high five there. That's called the tag five, because that's reminiscent of the TAGSAM arm that's eventually going to retrieve a sample.
So we are here. We have arrived at Bennu. Arrival was officially December 3rd of 2018. And that was a morning I woke up and saw an event on my calendar that I put there a decade ago. So it was truly a great day for us. And a lot of the uncertainty has been removed about this mission, right? One of the things that's characteristic of OSIRIS-REx is that we're going to a target that we've only seen through our telescopes. Arrival is one of the greatest moments of my career. I remember the very first images that came in. And, you know, we had been targeting this asteroid since 2005. So over 13 years of planning and plotting and dreaming about this asteroid. And we first saw it just as a tiny point of light moving across the background star field. And if you didn't know what you were looking at, you would never have spotted the asteroid because it looked like just any other star. But we all knew exactly where to look in that image. And then as you started to blink and we saw this thing move across, and I will never forget that feeling. It's like, it's real. It's really there. There really is something in space, and we know where it is, and we're on our path to rendezvous with it.
One of the most challenging aspects of pulling together that beautiful global mosaic of Bennu was getting the right data to make a mosaic. So before we even had the images that we stitched together, a few hundred in total, we had to make sure that we were taking images of the surface that were lit at just the right conditions so that you could see small shadows that would outline those particles, and also that were taken at sort of a straight on angle, or as straight on as we could do with our spacecraft, so that you didn't get a lot of distortion. Once we had all of that data, you're dealing with just have, you know, 1 million pixels or more. It took a lot of effort, but it looks like a very seamless map of Bennu. It's also the finest spatial scale that we have ever mapped a planetary object, which is pretty impressive.
We went through a very rigorous sample site selection campaign, and we had 3 driving criteria. We had what we called the deliverability, which is how tight of a spot can we get that spacecraft into. We were looking at craters that were about 20 meters or 60 feet in diameter, just the size of a small parking lot, and the spacecraft's about the size of an SUV. So it was a really tight fit, especially compared to what we originally designed to. The second one was safety. Even if we could get into one of those tight spots, would the spacecraft survive? And we were particularly worried about tipping over and flying away into one of the many giant boulders that dominate the surface of the asteroid. And then the third one was sampleability. If we got the spacecraft there and it was safe, was there anything on the surface for us to pick up? We were looking for particles about 1 inch or 2 centimeters across or smaller. And there's very few patches of material like that on Bennu's surface. So we kind of evaluated all of that. In the background was a parameter we called science value. But the good news was everything on Bennu was scientifically valuable. We saw water-rich clay minerals, and we saw organic molecules, which are 2 of the prime types of material that we were trying to collect. So in the end, you know, we kind of used the basketball tournament analogy, and we started with about 16 sites. We called them the Sweet 16, and we put them up against each other, and we evaluated how much fine-grained material we estimated was there. And we couldn't actually see the fine-grained material, but we could see where the big rocks were not, what we called the unresolved patches of the surface, and we assumed that there was fine particles there that we could pick up. We eliminated half down to the Elite 8 and down to the final 4. And when we had the final 4 sites, we performed a series of low-altitude reconnaissance passes to kind of do a safety check. And that very quickly revealed that 2 of the sites were quickly out of contention. One of them was simply just too small of a crater, and it looked a lot like one of the other sites, so we were able to eliminate it. And the second one looked really good. In fact, I thought it was the leading contender going into that phase, but it turned out to have a lot of fairly large rocks with the fine material interspersed in between it. And that one was gone. So we were down to 2. One we called Osprey and one we called Nightingale. Both of them about 20 meter or 60 feet diameter craters. One near the equator, Osprey, one in the northern hemisphere, Nightingale. And it turned out to be kind of a contest. Osprey was safer, but Nightingale was more sampleable. And also the science looked better there. It was darker, redder, it looked fresh, like recently exposed, so not modified by the space environment. When we pulled the board, we had a site selection board, my heart kind of sank when Flight System and the Goddard Space Flight Safety engineers voted for Osprey, because I really wanted But the Tag Sam team and the science team were voting for Nightingale, so it came down to me. I had to make the final decision.
Hello, and thank you for joining us in the booth here at AGU, the American Geophysical Union, for this special edition of NASA Science Live. Today, we have a big announcement from the OSIRIS-REx mission. OSIRIS-REx is NASA's first mission to retrieve a sample of an asteroid and return it to Earth. And we're going to find out from where today.
So I stepped away from the meeting. I kind of walked out and I said, you know, I have to go with the science, right? I have to go with the science. It's what we came here for.
Dante, do you want to tell us which one you've picked?
I will. So I'll say that just thinking that we're going to get this sample back to Earth sends chills down my spine. So the winner of the OSIRIS-REx Site Selection Championship is the Nightingale site.
All right. Make some noise, audience.
And I want the material from Nightingale almost like it was calling to me. So I made the final decision. We're going to go in. The safety was acceptable. Lockheed Martin agreed that they could sample that area, and the science is what made the decision.
It was a decision that had a lot of stakeholders, and a lot of people had to come together and make their case before a decision was eventually rendered by our principal investigator, Dante Loretta. And so I remember during the sample site selection meeting, Dante turned to those of us who were scientists on the team and asked what our opinion was. And I think I was the first person who spoke, and I was just like, Nightingale. It has the organics, it looks fresh. Like, if we just put our science hats on, that is where the value is.
Nightingale and Osprey were always pretty high on the list, but in my mind, it wasn't clear. We had some fascinating sites to choose from, including a few sites where they were very small sites, but it looked like there was some really fine-grained material there, but clearly they were just too hazardous for the spacecraft.
What is the biggest challenge of the site?
So the biggest challenge of the Nightingale site is those large boulders that are off on the eastern edge of the crater, because that tallest one, I colloquially call it Mount Doom, because it has the classic kind of peak shape that we're familiar with from the literature. That's about 7 meters tall, and then when you're down at the bottom of the crater, that's another 3 meters. So we're talking 10 meters or 30 feet. So it's a substantial building-sized obstruction, and we're trying to get into a crater that's on the order of a few parking lot spaces wide. So we are doing a really tight job parking that, and we're aware that we have hazards around us. So precision navigation to that sampled material is our biggest challenge. So all we have left to do to deliver on our promise to the agency is get that sample safely back to the Earth, get it into our laboratories, and answer the fundamental questions about the formation of our solar system and why Earth is a habitable world.
The pandemic has changed the way we lived our lives. Masks and social distancing have become a way of life.
As the whole world was coming to grips with the pandemic in the March timeframe, this team was in the midst of preparing for the checkpoint rehearsal that would take the spacecraft only 65 meters above the surface. So we had to rethink the entire way in which we were going to do that rehearsal with only a skeleton crew here in the building and with many of our team members remote.
I think the hardest phase of the mission was in spring of 2020 when the COVID pandemic hit. It was a scary time. And we were exhausted. And I would say probably by April, about a month after the lockdown, I wasn't sure we were going to be able to do it. And it wasn't because of the technical challenges, but it was the stress and the human factors that I was really starting to worry about.
Now, the main event is happening in about an hour. This is called TAG. Can you explain to us a bit why it's called TAG?
Yeah, today we're tagging an asteroid, and TAG is an acronym that describes our sample collection strategy. We're going to send the spacecraft down for a short duration contact with the asteroid surface, anywhere between 5 and maybe as long as 15 seconds. So we call it a touch and go, or tag an asteroid.
And that sample site we're going for today, Nightingale, it's just a few meters in width. Just take a step back for a second and put yourself in the shoes of some of those engineers on this mission. And imagine trying to park a spacecraft on an asteroid 200 million miles away, in a space no larger than a few parking spots. As if parallel parking on an asteroid isn't hard enough, imagine also trying to dodge hazards like rocky boulders as you're making your descent down to collect a sample. And on top of that, the team has actually programmed the spacecraft to steer itself down to the surface.
We mapped the surface of Bennu to unprecedented resolution of 2 centimeters per pixel, which is better than what we've done on our own Earth and Moon. So it was a huge Herculean effort to get to this point where we're comfortable handing the maps and the keys over to the spacecraft to get us down into this small site today.
So right behind me is the MSA, the Mission Support Area for OSIRIS-REx. And today it is filled with very excited people, the scientists, engineers, and technical specialists who've worked on this mission, in some cases, for more than a decade. So back there is Gary Napier from Lockheed Martin. He's right in the middle of it all. So Gary, what's the feeling in the room?
Michelle, like you said, I am just right behind you, about 20 feet. We're here in the larger Lockheed Martin Mission Support Area, where we're operating 6 of NASA's spacecraft around the solar system, 4 of them at Mars, 1 of them at Jupiter, and this one right here, OSIRIS-REx.
So it's important to understand that the spacecraft is actually literally on the other side of the solar system, over 200 million miles away from the Earth. So any signal that we were to transmit here would take over 18.5 minutes to reach the spacecraft. So when we get these signals back, we're actually seeing things that happened in the past at the asteroid. Earlier, we departed our orbit around the asteroid, so we're flying over the sunlit side of the asteroid, taking images for the onboard guidance system called natural feature tracking. A couple other key events that have taken place already is the spacecraft has deployed its robotic TAG-SAM sampling arm, so the arm is ready, in position to collect that sample. And we've turned on and started collecting science data from one of our science instruments, the Otis thermal emission spectrometer. The spacecraft has already moved into its second natural feature tracking attitude and is getting onboard positional updates as we speak. And I can tell you, everything is going exactly according to plan right now. It looks really good.
Now, remember that this is a historic event. Today's endeavor will be the first time the space agency has ever touched the surface of an asteroid, collecting a sample of this pristine ancient material, a scientific treasure far more precious than gold. Let's talk a bit about why working in this low gravity environment makes it tough to get a sample, because you might think sort of at first you could just take like a robotic claw or a robotic arm and scoop something up, but that's not going to work in these conditions.
That's exactly right. The microgravity of Bennu provides a challenge of sampling that we don't normally face on Earth. You can imagine trying to use a shovel or a scoop on Earth and the ground pushes against you, but the gravity keeps you on the ground. On Bennu, the surface gravity is thousands of times lower than on Earth, so if you pushed a shovel or a scoop into the ground, you'd push yourself right off the surface. So we had to come up with a technique that worked in the microgravity environment and that could work in this tag architecture, this touch and go architecture of just a few seconds long.
So I understand the next big milestone we're looking for here is something called match point.
That's right.
So what happens at match point?
Match point is the final maneuver that the spacecraft performs by firing its thrusters. That's where we become centered over the Nightingale sample site and begin that final descent down to the asteroid surface. And the spacecraft is solely focused on its safety calculation and the decision on whether or not it's going to proceed down to collect that sample.
Attitude control system has transitioned to touch and go mode.
Right, spacecraft getting ready to make contact with the asteroid surface here.
OREX MSA on OREX off. OREX is descending below 25 meters.
Okay, we're getting really close. And I want to remind you, it's the 5-meter crossing.
Yeah.
That's the really critical one. We're only a couple minutes away from that. So the spacecraft has one key decision left to make. It's calculating right now the probability that it's going to come down either on a hazardous area, as we defined on that hazard map, or in a safe area. So we may, at 5 meters, the spacecraft may decide that it's hazardous and it's going to back away, allowing us to live the tag another day. So to me, all my senses are on that call out right now.
Yeah.
I really want to hear that we are go for tag.
Position uncertainty is 0.5 meters. Predicted tag lateral offset is 1.7 meters. Hazard probability is 0%. Tag lateral velocity is 0.2 millimeters per second.
Oh my God.
Tag vertical velocity is 10.2 centimeters per second.
That sounded really good.
Yes.
So it sounded like the hazard map calculation looked really good. We're coming down on a green area.
MSA on OREX off. OREX has descended below the 5-meter mark. The hazard map is go for tag. Contact expected in 50 seconds.
We're going in. We're going in.
Touchdown to Sampling is in progress.
Oh my gosh, we're there, folks. That was amazing. I mean, I don't know if you saw the team here, but they just kind of blew up. It went from being steely-eyed to like celebrating the Super Bowl. Congratulations. How you guys feeling?
Transcendental. I mean, I can't believe we actually pulled this off.
OREX MSA on OREX op. Sample collection is complete and the back away burn has executed.
All right. The pyro bottle's fired, so tag SAM operated. The back away thruster is fired, so we're safely moving away from the asteroid surface. The spacecraft did everything it was supposed to do. We did it. We tagged the surface of the asteroid, and it's up to Bennu now to see how the event went. It's almost hard to process everything that's happening right now. It's overwhelming pride in this team and everything we've done to get here. I couldn't really have anything better to say about this group of people.
We are here live after some excellent news. I'm here with an exultant Dante Loretta from the University of Arizona. So one more time for our audience out there, explain when we know we'll have a sample.
A little overwhelmed right now, Michelle, I have to say. It's been pretty intense several minutes here. I can tell you that everything went just exactly perfect, which is kind of the hallmark of this team. We have consistently beaten expectations over and over again. We have overcome the amazing challenges that this asteroid has thrown at us, and the spacecraft appears to have operated flawlessly. We don't know how long we were in contact with yet. That's some reconstructed information that we're gonna have to put together over the next few hours as the data come in. We backed away successfully from the asteroid surface. The team is exuberant back there. Emotions are high. Everybody is really proud. We have some work to do to determine how much sample that we have collected. The next thing that I'm going to be looking for is once the spacecraft cools off, it probably got pretty warm as it approached the asteroid surface, so it needs to get rid of some of that excess heat. It's got to get those solar rays back onto the sun and get power positive. Once it's stabilized, it's going to point that high gain antenna at the Earth, and we're going to start bringing that data back. And those SAMCAM images are going to tell us an enormous amount of information about how the events of today went.
It's going to be a long, hopefully happy night for all of you as more data comes in. Thank you so much. It's been such an honor to be with you.
Thank you. Thank you, everybody, for a great evening. And kudos to this team. It's an amazing experience.
Oh, wow.
And history was made tonight.
Hello, everyone. I'm Nancy Neal Jones from the Office of Communications at NASA Goddard Space Flight Center. Yesterday, NASA's first asteroid sample return mission, OSIRIS-REx, successfully made contact with the surface of asteroid Bennu to collect a pristine sample for delivery to Earth in 2023. To share some remarks with us and to tell us more about what happened yesterday and what's coming up for the mission, we have with us today Dante Loretta, OSIRIS-REx Principal Investigator, University of Arizona.
So yesterday was all about monitoring this real-time telemetry from the spacecraft as we watched the events unfold 200 million miles away. And the question that came up over and over again in that live broadcast was, when are we going to get the images back? When are we going to know how the sampling event went? I can tell you, a lot of us were up really late last night. We were watching the images come down one by one. By about 2 a.m. here, local time in Denver, we got what I call the money shot, where we saw TAG-SAM contacting the surface and then the effect of injecting that high purity gas down into the asteroid regolith. I must have watched it about 100 times last night before I finally got a little bit of shut-eye. And then I dreamed of a wonder world of Bennu regolith particles floating all around me. Well, like everything on Bennu, a nightingale was unexpected in the way it behaved to the contact from the spacecraft. It's fun to go back and look at some of our early animations where you can see the TAG-SAM head pushing firmly onto the surface, kind of like hitting a pad of concrete. There's a little bit of grain and dust that gets kicked up. And you know, we didn't make that up. We tested TAG-SAM dozens of times, including in microgravity on NASA's C-9B microgravity testing aircraft. And that's what it looked like. TAG-SAM pushed down onto the regolith bed, a few little particles floated away, kind of like coins flipping in slow motion. You could hear the rumble as the gravel got ingested into the TAG-SAM head, and then when you pulled away, there was a tiny little divot underneath what TAG-SAM was. And we really thought Bennu was going to behave just like the test chambers did. But no, it was completely different. There was almost no resistance whatsoever from the asteroid surface. The TAG-SAM plunged in. It was like dropping into a pool of water. And we were deep into the asteroid subsurface even before that gas fired, and we just kept going. If we hadn't fired the back-away thrusters, we think the spacecraft would have just disappeared like into a pool of quicksand. So as a result of that really soft, compliant surface, the gas from TAG-SAM and the thruster plumes from the back-away burn excavated an enormous crater, 8 meters or about 25 feet in diameter, way bigger than anything we expected. our glorious moment. We safely contacted the asteroid surface, bury the tag SAM head, and fire the gas, and you will load that thing up. Turns out we did too good of a job. So, we backed away. 2 days later, on October 22nd of 2020, we put tag SAM through a photo shoot. All kinds of different camera angles and lighting conditions, just trying to get some hint. Was there any sample that was collected in this amazing event? It looked like the tag SAM head was literally spewing material into outer space, and panic shot through me at that moment. And I was like, oh man, we're bleeding. We're losing sample at an enormous rate. About 10 grams were visible in that one shot. That was, 1/6 of our total mission requirement in a few seconds that we were seeing escaping from the tag SAM head. The good news was, the reason we were leaking material was because we had collected so many large stones that we were jamming open the safety valve meant to keep everything inside the collection chamber. So we got permission from the agency to go through rapid stow, quickly got the tag SAM head into the sample return capsule. And fortunately, we were able to go back to Bennu in April of 2021 to get some great imagery and spectral data of the surface to really quantify the nature of that disturbance. When we designed the mission, we did not plan to go back and image the tag site after sample collection. We thought this is such a risky maneuver, get the goods and get out of Dodge kind of approach. But after that amazing and dynamic response of the asteroid surface, I couldn't leave it alone, right? I was like, this just keeps bothering me. We have to understand what we did, and we have to document it for science and for future asteroid explorers to understand why this behaves so differently. When we estimate the strength of the particles that we see on the surface, there's no way they would survive passage through Earth's atmosphere. They would simply disintegrate, forming a giant fireball. So I have high confidence that we're bringing back the kinds of material that literally, physically cannot make it to the surface of the Earth as a meteorite.
All stations, the ADM burn is completed. We have a nominal ADM burn, and we're bringing the samples home.
The science speaks for itself. I mean, we're bringing back hundreds of grams of pristine sample from a body that hasn't been touched and is relatively unchanged since the beginnings of the very solar system. So the benefits to science are just astronomical. But the benefits to engineering, which is really what I'm interested in, is to me just as fascinating. It's like we're really pushing ourselves, the challenges, the things that we can do with the technology that we have. It's demonstrating our ability to deliver something from space to the ground safely and accurately. That's, to me, motivation enough to do these types of missions, well beyond even the science information that we'll gain from it, which is just invaluable to humanity.
And then really, the reason I answered the phone call, the reason I signed up for the mission, the reason I put in all of this hard work is finally going to come to pass. We're going to get pristine samples of carbonaceous asteroid in our laboratories and really go after the big question. Did these objects deliver the seeds of life to the Earth?
I'm not sure it's possible to identify one single person who will be the most stressed out. I'm sure that our principal investigator, Dante Loretta, will be very stressed, but also very, very excited, as this is the culmination for him of almost 20 years of work. But we have so many people on the team who are so invested in this and really, really care about the sample and who have been working on this mission for years and years and years. So I think we're all going to be a combination of very nervous and very excited.
Yeah, we're going into endgame here, after almost 20 years.
So the sample return capsule is landing at the Utah Test and Training Range west of Salt Lake City, and this is an Air Force test range. It's a wide open area, basically a dried salt flat, dried lake bed. It's free of obstacles. It has lots of DoD tracking devices around there, and it's a controlled airspace. It's a great place to bring something back from space where you need a large landing footprint. Right now, we're only 60 days away from the sample landing. We're working on all of the final logistical details of getting all our people out to the site to do the recovery. We just completed a training last week. We're going to do another rehearsal in August, which will be our final rehearsal. A lot of moving parts right now.
When I found out I was going to be the ground recovery lead, I was very excited. It's rare that you get to be involved in some sort of a project that brings something back from space, and to be in a role where you get to oversee all of those operations and make sure that it happens without a hitch is just a really exciting opportunity. And we have to make sure that everybody is trained, that everybody agrees with the way that we're going to do things and is ready to go. And it's been fantastic because everybody's pulling in the same direction and we're ready to recover this.
So a very important requirement for OSIRIS-REx is to get the sample into a clean room as quickly as possible, because we're trying to maintain the pristine nature of the sample, make sure it doesn't get contaminated from stuff that's in the Earth's atmosphere or on the ground at UTTR. So the recovery team is designed to make that recovery happen as soon as possible. There's a couple of technicians from Lockheed Martin, there's a couple of curation specialists from the Johnson Space Center, and there's a couple members of our science team. And then there are 2 members of the Air Force that are our on-scene commanders that are helping us navigate the range. That team will fly out to the capsule landing site on 4 different helicopters, and they each have unique tasks of securing the capsule, making sure the area is safe, sampling, taking soil and air samples from around where the capsule landed to look for possible contaminants, and then get the capsule packaged up as quickly as possible to fly back via helicopter. So we're very concerned about the safety of the recovery team, and one of the possible things that could go wrong is if the batteries start on fire once the capsule lands. We don't expect this to happen, so one of the first things we're going to do when the capsule lands is one of the Lockheed Martin technicians will go up to it with a sensor to detect noxious gases that would be released if the battery were cooperating. And if we don't detect that, then we can proceed with the rest of the procedure. If we do, then we have to stand back and wait for the situation to clear. So we fully expect when the sample return capsule to hit the atmosphere that it will release the parachutes and descend slowly at that 11 miles per hour. But there is a chance that if something unexpected goes wrong, that the parachutes won't deploy. In that case, the sample return capsule will have a hard landing. It'll go very fast, it'll hit the ground, it'll likely rupture the sample return capsule. That's a very low likelihood scenario. We fully expect that the sample return capsule, the parachutes will deploy, everything will work as expected, and we'll get that nice pristine sample in a very protected, enclosed sample return capsule. So the spacecraft is approaching the Earth at a speed of over 27,000 miles per hour. It'll release the capsule at just the right moment to intersect the Earth's atmosphere. We only have one chance to do this. We can't, wave off and do it the next day. If there's bad weather, if there's a snowstorm at the Uter, when we are getting ready to release the capsule, we will still release, and we will do our best to get to the capsule as quickly as possible. But this is truly a critical event. Everything has to happen on time in order to be successful here.
The team prepared for virtually every weather condition that we could think of. A number of our rehearsals we did in the rain. We also wanted to be prepared in case there was muddy conditions. So we actually built a custom mud pit and put the capsule inside of it and practice recovering it. We also practice under extreme heat and very windy conditions. So we've made sure that we've practiced in every possible condition that we could see out here today.
Not an optimal scenario, but I think we can operate in it.
On September 24th, the sample return capsule is going to land in Utah at the Utah Test and Training Range. And from there, we will have to track it down a little bit, but we'll be tracking it in flight to get to it as quickly as possible. Our field team will go with helicopters and bring that sample return capsule actually to a portable clean room or temporary clean room we're going to have set up in a building right there in Utah.
The capsule will actually be carried back to a clean room under a sling from the helicopter, a 100-foot long line, and that allows us to pick up the capsule from the ground via helicopter, fly it back to the hangar, and drop it right outside the front door.